known for doing that. Like,
Quite a bit, so yeah.
yeah, totally. Yeah, that's like your
The
thing.
thing is, it will be mostly after the break.
I just need to turn it on because it takes some time.
Yeah, we won't be doing it in the first half an hour.
Okay.
Although you may still want to turn it on for better reference to the picture I'm going to be using. All right, folks. Let's get started. So, after today, all of you should be able to tune the controller for the case with the response curve to a step change doesn't have oscillations, maxima or minima. If it's sigmoid, you should know how to tune the controller. Oh, bracket is missing. I'm giving the equation in terms of y. Y is the actual sensor output. Y prime is the deviation variable. The difference is, if we talk about y, we add y naught. If we talk about y prime, the y naught is not there. Also, I want to make sure, close the door, I tend to lock myself out.
Did you guys do that?
Also, I want to point out that everything we're doing is in the notes that I have posted with one difference. The notes equations do not have T naught. In other words, T naught is 0. So what you find in the notes is T less than D, and T greater than D, and T minus D here. That's not a problem. The two equations are totally equivalent if you rescale the time axis by subtracting from every, and have to do it from every measured time measurement, the time of the step change. Okay? Clear? So for example, if I have a response curve, and here is my delta y, and I'm measuring T63, 63% of that, here, that's T63, measuring T28. Yeah. 0.28 delta y. Come here, that's T28. If you use the equation we derived in class, you use the actual time. So let's say this T28, let's say, is 42, and this, let's say, is 67, and let's say T naught, time of step change, is 35. Okay? So using T naught 35, 42, and 67, you use those equations. So you're going to use the class notes equations. You subtract 35 from both the 42 and the 67. So the 42 becomes 7, and the 67 becomes 32. Clear, everyone? So you use these equations with T naught 35 using the actual times measured here. Or you use the equation that use T naught equals 0 by subtracting T naught from every time measurement. Carlos, are we clear?
Yeah.
Okay. So what I plan to do today is first take an example from a previous example and use that to do first, let's say, either Exxon or Smith-Corripio three-point method. Then create a three-point method from one of you and get GU with that. Then learn the absolute best way to get the first order plus time delay model, but of course this is also the most involved method, and that is minimizing the sum of error squared regression to find the parameters. And after the break, we are going to be going to the game. We're going to find first order plus time delay model for the game, and then we're going to talk about Q. All right, any questions? All right, so let me pull down the screen. And we go. So if you go to the previous exams and look at exam 1B, for example, 2012, I believe. Oops, no, I meant 1A. Wrong one. 1A, 2012. You see all my exams, and absolutely guaranteed, a major problem of exam 2 will be giving you a response curve like that and asking you to find the first order plus time delay model and perhaps tuning a control. Okay? You can put that in writing. You already know what major exam problem is going to be in exam 2. So let's read this problem. Dim the lights. So at time 45 seconds, the temperature of the coolant of the reactor was decreased, and notice the bolts. The bolts are to help you pay attention to things. by 40 degrees. The reactor temperature measurement had the response shown below. So why is reactor temperature measurement calibrated to translate the temperature measurement? I'm not going to do the slope method because of time, although I'll tell you what, might be time to spend.
Do it.
Let's also do the standard. I'll tell you, I'll do the standard slope method, and instead of doing the standard three-point method, I'll do a modified three-point method. So you have slope method, a modified three-point method, and then the better method. So first, you see the first problem was slope method. You see only 10 points, but remember that's out of 50 points. So that was just that part was 20 points, and you can see this was 40% of the exam. Okay, you can expect similar weight in the final exam. Don't mess it up. From a practical point of view, this is the one thing I want to feel absolutely sure that each one of you is able to do tomorrow if you are in a job and you need to tune a controller. You should be able to get the response curve, and you should be able to get the first order plus time delay transfer function, and you should be able to use one of the methods we learned in this class for tuning. All right. So, since I'm going to draw on it, I need to capture this picture so I can draw, so I'll capture it in Paint. So, Control the screen should work. If I go to all programs, where is accessories? Oh, no, accessories. Paint should be here. There it is. Control V, bring it in. Good. Okay.
Is this the ruler part? You're just going to do it in Paint?
Yes.
Okay.
That's why I'm going to do it in Paint, to do the ruler part. Exactly. So, one. Slope method. That and all, we need to find the first order plus time delay transfer function. What does that boil down to? Finding the three parameters, k, tau, and d. It's a sigmoidal response curve, so we can definitely do first order plus time delay. So for all methods, G u of s is k over tau s plus 1 e to the minus ds. Okay? So click on the line. Let's make it not too thick, but make it a little bit bigger than the default. So, first of all, let's talk about k. So, k is delta y, the change in the measurement, divided by the change of the input. If it was a disturbance, transfer function, it would be delta dr. Okay? Same method, whatever the input, manipulated input or disturbances, we would find the transfer function the same way. So, what is delta y? Well, it's new value minus original value. So, new value 140, so negative 10 is of course correct, minus 150 original value. And the input changed by 40, right? So delta u should be 40.
Is it negative 40?
This point, always make the mental check. What is the input? What is the output?
Should be negative.
Input is temperature of coolant. Output is temperature measurement of the reactor. If I increase the temperature of the coolant, which way would the temperature of the reactor move? Up. If I decrease, it would move down. As a matter of fact, I decrease. If they move in the same direction, K should be plus. I emphasize, you're going to be very unhappy with your final, and Rim, don't complain. I may give a 0 for messing up just a sign, because that sign may blow up the reactor. So, clearly it should be positive. If I put 40 here, I'm getting negative.
That 40 should be negative, right, at the bottom?
Exactly. I was nice. I put the decreased in bold. If it decreased, mu minus old is negative. So it should be minus 40. So I didn't tell you not to write it yet, because you can just add the minus. Okay? So that's plus 0.25. And whatever method we are using, that's always the case for K. If you have actual experimental data which have measurement noise, take at the place where it has leveled off and average a large number of values to find the new value of 1 in your steady state. Clear, everyone? Now, next in the slope method is the delay. How do we get delay? Delay is T corner minus time of step change. So for T corner, I draw the slope line, and remember, time corner is the time that slope line intersects the original steady state. So if I'm going down, it's going to be on top. If I'm going up, it's going to be on the bottom. All right. So, what would be a good slope line? So I put here the line, I put the thickness. Is this a good slope line? That's terrible. That's not tangent.
Why not? It's cutting 1 point.
Yeah, I still don't know how
A tangent line
I know.
it hits at one point. Like,
coincides. There's always a straight line portion. You go from curving one way to curving the other way. There's a place where it's a straight line portion, where the first derivative, so where the second derivative, sorry, is 0. And if and that's definitely not correct. It's at about the right point, but it's not drawn correctly. And it will not have a correct coordinate. Undo. How about this one?
Oh, you have to size it. Wow. Jeez.
Okay. Is that a good slope line? No. Notice at the point, suppose tangency, and this is a tangent line, but it's a tangent line not at the point of inflection. It's a tangent line at the wrong place. It's at the wrong place. You notice experimental data on the same side of where I drew it. If I draw it at the correct point, at the inflection point, it should be on either side. That's not it. All right, now here is my drawing skills being challenged somewhat. With a ruler, it would be a lot easier than. Yeah. All right. That's excellent. Wow.
That's touching the whole line.
Almost. That's ideal. If your curve looks that good, that's perfect.
that's what it's supposed to look like?
Yeah,
Yes.
that looks like a Taylor expansion. That is almost the line.
It's a tangent line at